Okay, in this video, we're going to have a look at how we can use transformers for our own applications. And to do so, we're going to use a library from Hugging Face. When you try to implement some transformer-based applications, you must encounter these Hugging Face transformers. Therefore, here I'm going to show you how you can use these transformers libraries for developing your own applications. And using Hugging Face transformers is quite easy. You just need to install these transformers and these data sets. If you want to use these libraries in your computers, then you just need to remove these marks here and then just pip install datasets and pip install transformers on your terminals. So in this Colab environment, if you want to run some terminal commands, then you should put this exclamation mark at the front. Then this will be run as terminal commands. So first, let's install these two libraries or packages. Then most of the packages are already installed. And after that, I'm going to run some default code for our tutorial. Okay, we're all set here. And let's dive into today's topic. Part 1 or part 0 is about common pattern for using Hugging Face transformers. How can you use these transformer libraries? This is the picture of common pattern. What we usually do is we are given a raw text. However, our model cannot process this raw text right away because, as we saw in our slides and previous sessions, we need to somehow turn this input text into a list of numbers. And we basically use word embedding for text input or text data. And we perform that process using tokenizer. And this tokenizer changes this raw input into a list of IDs. And then we put these IDs into our model. And our model outputs some output. And then we post-process these logics, or it could be anything defined by the model. Then after we process these logics or the output from this model, then we can get what we want. This is basic pattern for using Hugging Face transformers. Okay, let's see what I mean by these. Here we're going to import auto tokenizer and auto model or sequence classification. After this auto model, we can specify the model's output type. If it is for sequence classification, then this model will output corresponds to sequence classification. And we can specify different types of outputs. We're going to have a look at the list of outputs we can have, the types of outputs we can have. We can have like 4 question answering or 4 multiple question or 4 masked LM, things like that. Therefore, this transformers library package offers various types of model configuration. And we need to initialize this tokenizer. And we can call pre-trained method like this. And what kind of pre-trained model should you use here? And this is the website you can have a look at, where all kinds of models are listed here. There are more than like 400,000 models already. Like some models are from OpenAI, Berkeley, Intel. They all upload their pre-trained models here. And you can search different types of models like multimodal, computer vision, natural language processing, audio, tabular, or reinforcement learning, like this. So depending on your application, you choose these pre-trained transformers and fine-tune or use them as they are for your applications. Okay. Here we're going to use Liebert, Sentiment, Roberta, Large, English. And we also need to define our model as auto model for sequence classification. And from trained, and we're going to use the same model. Because if we use different tokenizer than the model, then they are not synchronized. And these raw input turned into input IDs through this different tokenizer will not have any effect, any meaningful effect on this model. So we need to match the same type of tokenizer and model. Okay. And when we run this code, these codes will automatically download the pre-trained weights like this. Okay. Here, because we are doing sentiment analysis, our model will output 2 values, one for positive, the other for negative. So it will just try to classify whether the given input is a positive sentence or negative sentence. And our input example sentence is, I'm excited to learn about Hugging Face transformers. And let's first tokenize this input. Then we're going to pass this sentence into our tokenizer. And you can pass a auxiliary parameter. Here you can specify whether these tensors are going to be in the form of NumPy or PyTorch or TensorFlow, anything. So it is up to you. You can specify the return tensor's type or not. Okay. Then what we are going to do is pass this tokenized inputs to our model. However, our model does not produce whether this is positive or negative sentence. However, it outputs logics because it is sentiment analysis model. Like different models, like for classification or for masked language model, it will output different types of tensors. Okay. Therefore, we're going to turn the output into some human recognizable labels. Because we return tensors in the form of PyTorch, we need to use Torch. And even though we haven't talked about PyTorch in our class, it's very similar to NumPy. And Torch also has argmax like this. And that's what we are going to use. Okay. And let's print out our outputs. So we're going to basically print out the raw input and the tokenized input and the model output. Okay. There was a typo here. So the raw input looks like this. I'm excited to learn about Hugging Face transformers. And this tokenizer tokenizes this input into input IDs and attention mask. And because we have to give attention to all these words, attention mask consists of a list of ones. And the model output is logits, tensor of logits. This is the score for negativeness, and this is the score for positiveness. And the prediction is positive. Okay, this is the basic working flow of Hugging Face transformers. Okay, this was basic usage of Hugging Face library. And let's have a look at a more detailed usage of tokenizers. Here we're going to import two different tokenizers. And there are various types of tokenizers you can import from. And here I'm going to show you three types. Auto tokenizer we've already seen, and distill BERT tokenizer fast, and distill BERT tokenizer. And the usage of these tokenizers are basically the same. We just call from pre-trained method. And then we're going to call distill BERT tokenizer fast. And then auto tokenizer from pre-trained like this. So let's call these three tokenizers and see the difference. As we can see here, this basic distill BERT tokenizer is distill BERT tokenizer. And they have some special tokens like pad, unknown, class, separation, and mask. And DistilBERT tokenizer fast has similar configuration. And this auto tokenizer in default initializes DistilBERT tokenizer fast. And what is the difference between DistilBERT tokenizer and DistilBERT tokenizer fast? This is written in Python. And this is written in Rust, a very fast language, something like C. Although the interface is Python, it's basically written in Rust. So this one is faster. And auto tokenizer doesn't care about which tokenizer you need to import. However, it automatically matches the tokenizer you need to use. And this is very simple and easy to use. Okay, so in most cases, you're going to use auto tokenizer rather than specifically call one type of tokenizer. And this auto tokenizer in default initializes this faster version because this is faster, right? And this is very convenient. So you are going to use auto tokenizer most of the times. Okay, that was how we initialize tokenizers. And let's have another input sentence. In fact, tokenizer tokenizes the input sentence and you can get access to this tokenized inputs in two ways. This tokenization returns a dictionary, and it contains two things. The first thing is the list of input IDs, and the second one, the other one, is the list of attention. And you can get access to the input IDs in two ways. You can use dot operation like this, or just access to these input IDs as you do for dictionaries like this. Okay. And tokenization takes a few steps. I'm going to show you what I mean by those two. I'm going to show you what those few steps are. And you can convert tokens to IDs like this. We can decode this tokenized input using decode method like this. Okay. Let's print out our results. What they are together. So the first step is tokenize. And after tokenization, we convert tokens to IDs. And then we add special tokens. There are some errors. There was a typo here. Okay. First, the raw input looks like this. Hugging Face transformers is great. And this raw input sentence is transformed into tokens. And what are tokens? The minimum block, minimum meaningful block. So this ha has a meaning and ging has another meaning. Face is another token, transformers is another token. Token, token, token. And when you convert these tokens into IDs, we saw some dictionaries, word dictionaries. And in those word dictionaries, each word received an ID. And we convert these tokens into IDs. And that's not the end. We need to add special tokens. In front of this token list, we need to add CLS token. That is 101. And at the end, we also need to add separation token, which is 102, like this. And after decoding, it looks like CLS separation. We saw in the BERT case that we need to separate sentences by this separation token. Okay, so this is the process of tokenization. Okay, so this is the process of tokenization. Okay, and you can call encode like this. And this will automatically tokenize this input sentence. And you can get number of tokens like this. IDs through input dot IDs. And you can also print out tokens. Input tokens like this. And special tokens mask. Input special tokens mask like this. Okay. So you can do various things like this. And you can get special tokens like this. So these are for the raw sentence. And the first and the last one is separation and class token. Okay. And you can also process multiple sentences at a time. Hugging Face, Transformers is great. And you can add a quick brown fox jumps over the lazy dog like this. And the dog got up and ran away because she didn't like foxes, like this. And then you can specify some arguments like return tensors, padding, truncation. Okay. When you do natural language processing, you will understand that this kind of pre-processing takes a crucial role, then as crucial as the model itself. So you need to understand the functionality of this tokenizer. Okay, this should be truncation. As you can see here, these paddings get no attention. However, the meaningful sentence get full attention like this. And you can get multiple input IDs like this, okay? And of course, you can decode batch. That you need to call batch decode rather than just simple decode. And you can skip special tokens like this. And this default batch decode decodes the sentence containing these special tokens. And if you skip special tokens, then it will just skip these special tokens like this. Okay. Yeah, that was about tokenizer. Okay, the next thing we're going to have a look at is the model itself. Initializing models is very similar to initializing tokenizers. You can either use the model class specific to your model, or you can use an auto model class. Okay, and as I told you, there are different types of models you can use. Like for masked LM or for sequence classification or for token classification or for question answering, or for multiple choice. And here, at this start position, you can use either auto model or specific model like distill BERT, like this. However, as I told you, I prefer to use auto model because it automatically matches the specified pre-trained weight to the model. Okay, let's see how we can initialize these models. As we did for tokenizers, we can use similar procedure to define our models. First, we import the models of interest. Auto model for sequence classification in our demo. However, you can change this for sequence classification part with for question answering or for multiple choice, depending on your application. And you can also specify the specific model architecture like distill BERT for, there are other classes like, as you can see here, like you can use Dino and other model architectures. However, here we're going to use distill BERT for sequence classification, like this. And then defining the model is quite simple. From this imported distill BERT for sequence classification, from pre-trained distill BERT base case. And here you need to specify the number of labels, like this. And you can also use auto model for sequence classification, like this. And when you run this code, it will automatically download the pre-trained weight, like this. Okay. And you can specify the model inputs. And you can put this input into this model as we did before, like this. You can also specifically input some different parameters like input IDs and attention mask. Like this. Okay. And these two operations result in the same result. And we're going to print out the model inputs, model outputs, and we can use softmax to this model logics. Then we get these input IDs and sequence classifier output. And the distribution looks like this. Okay. And you can train these models, as you can see here. You should probably train this model on a downstream task to be able to use it for predicting and inferencing. And here, because we specify the number of labels, it says some weights of this BERT for sequence classification were not initialized from the model checkpoint. And as you can see, as you can infer from this statement, the last hidden layer is not initialized with this distill BERT for sequence classification. We're going to specifically train down, fine-tune these weights. And as you can see here, the weights are not that well distributed. Okay, then how can you actually train? We first need to define the label. In PyTorch, we use tensor rather than array. In our NumPy examples, we used array. However, if you just replace this MP to torch and array to tensor, then we can do the same thing. And we define loss, cross entropy, and this label, then it will calculate the loss. And you can backward loss in this way. Okay. And you can also get some parameters like this. And we'll just print out just the first one. In this way, you can get the gradients by calling this backward. And we also get some weights like this. And we're going to have a look at how we can actually fine-tune these pre-trained models specifically to our applications. So wait for that. Okay. And the final thing I want to note here is that we can visualize the attention. By calling this pre-trained, we just specified the specific name of this model. However, when we add output attentions to true and output hidden states true, then we can get all the attention masks and we can visualize them. And when we do that, we better set our model as evaluation mode. When we set our model as train mode, then it will just store all the caches required for calculating backpropagation gradients. However, if we just set model to this evaluation mode, it will not store those caches. Therefore, the computation becomes faster. Okay? And to assure that there is no gradient, we can use this term. With torch, no grade. And from this model output, we can get hidden states. We'll just retrieve the first one and get the shape like this. And we also get attention. Output attentions. Okay. So as you can see here, we can get the hidden states and attentions like this. And let's print out the model output. Okay, you can get the output like this. And what you can do is, this is the code. You can visualize these attentions like this. Okay, let me show you the result like this. This is the input sequence. Hugging Face transformers is great. And this will visualize each attention map. And you can get, you can understand based on what logic this model results in this prediction, okay? So by setting this option for output attention is true and output hidden states true, you can visualize these attention maps. Okay. This is the end of this video, and from next video, we are going to discuss how we can actually use these pre-trained models for our specific applications, fine-tuning.